Hello everybody and welcome to another video. In today's video we're going to talk about the usage of initializer list in C++, its copy and move semantics, and when not to use it and when to use it, etc. And also how it works behind the scenes. So let's first start off by explaining or breaking down in great detail of what it is behind the scenes. As you can see, when we do size off on initializer list, it gives us 16 in 16. And this is regardless of what kind of type we define our initializer list as, or its elements. So this is what it is. It is a fixed array on stack where, depending on the arguments you put in, it is going to allocate the said fixed buffer size for the buffer on stack. For example, if you define your initializer list like this, let's say array, and say S1, S2, S3. So the compiler will turn this into, one second. So the compiler will turn this into something like this. And then you proceed to ask, why is it 16 bytes altogether? Because this buffer, if we take the size of it and we divide it by S, which is the holding element type, it is going to be definitely more than 16, especially when we change the size of this buffer on stack. But the reason that it is 16 bytes only is because it holds, and this is where you really gotta give the credit to the people of C++ community and whoever designed it. You really gotta give them a lot of credit for thinking about this. So it is essentially a struct that says initializer list, and then it holds, it's something like this, right? It's a template class T, and then it holds the beginning of the array, which is the start, and the end of the rear of the static array on stack. Or in this case, it would be just on stack, not to be confused with the static keyword here, which serves a whole different purpose and sort of takes your buffer on stack out of the current section of the code and tries to put it in the data segment so it is easily accessible. And it serves as a global variable more so, in simpler terms. So that is why it takes 16 bytes. It takes the start of the array, which would be S plus 0 and S plus 3 in this case. Or is it S plus 3? It's S plus 2 actually, because we have to count in the 0 index. So that is what it is behind the scenes essentially. So the compiler turns it into something like this. S and S2. But if you look at it more carefully, it's not even that, because a buffer on stack in C++ will prefill all of the data before we get to use that stack or that buffer. And that's just how C++ semantics work in this case. So to avoid this handicap, and it is truly a handicap in our case, as it can affect our performance greatly, as first we have to call all the constructors, and then we get to call the move assignment, which is not great at all. So in one of my previous video, we talked about static storage, and I took that piece of implementation, put it in this video, so we can use it to try to implement or to explain how initializer list is implemented. So essentially we have a buffer that uses unsigned characters, so we avoid calling redundant constructors and only call constructors when we actually need to. We also improve the implementation by not having a member function, but having a macro that for particularly moves, it would serve a much better purpose than this one here. This is because once you call this one, then you have to call the move constructor of your underlying T type. So to avoid that, and you can check it out in the video called C++ static storage implementation, why are we exactly doing this if you didn't get it from this explanation or just a high level overview. Oh yeah, I also made a mistake here, should be T. So let's now use the real static storage that avoids pre-initializing our user-defined struct or class and forces the pre-filling behind the scenes. So static storage S, and I'll say 3, and I will say array, and now I'll have add, I forgot the name of the, okay, so it's gonna take storage, it's gonna take item, and it's gonna take the type. This macro can of course be improved, but that is not the objective here. And take S. Now let's see what's our output. There we go. Now we avoid all of the nonsense, for lack of a better word, of having to prefill our buffer on stack, and now we jump straight to initializing our structs right out of the gate, and you can see that it works pretty well. So now let's compare the output of the initializer list, which is essentially going to be the same code. So it is the same. We have called the S constructor 3 times on int, and at the end of its scope we're calling it, we try to clean all that up, and we will call each and every single destructor or invoke each and every single destructor of the S in the initializer list. So with that in mind, we can deduce that the initializer list lifetime depends on really the current scope. If we try to copy around, and copy and move semantics are really treated as primitive pointer semantics in C++, because its underlying implementation is what we discussed it is. It's start and end pointers. So if you try to do something like this, initializer list S, array 1, array, there will be no enforced shallow copy of this array of elements at all. That is because the copy will be, we take the start of the array, we take the end of the array. So we can validate that with this assertion. Array.begin equals to array1.begin. So if they point to the same memory address, that means they are the same. So if I define my array buffer like this, and I try to copy it like this, it will take the start and end pointer and just not swap it, but assign it in the current instance of the static storage, or in this case, initializer list. So this makes initializer list essentially a primitive, because you can't really copy it and you can't really pass it around unless you're 100% sure that you're going to end it at that point of time, at that point of its life cycle, which will be the current scope. So if you pass it around, you can pass it around in a function, but you have to be really careful when it ends, when its lifetime ends. And also what's important to point out is, if we try to do something like this, let's say 4, and I want to modify the first element, I'm not allowed to do that. Why are we not allowed to do that? Well, it's for safety reasons. You don't want to pass around the initializer list and end up modifying it at some point. That means that the call has to go all the way back to its origin if we are talking strictly about recursion, and still take care of this S. And this is the kind of restriction they would make in order to have the start and end pointer immutable. And it is essential that they are immutable. So what do I mean by you cannot pass around the initializer list? So in my Ask class I did something like this. I have initializer list that contains the elements S, and then once I call this constructor, I will do a copy, or I can do a move here, doesn't matter because it's a primitive as we discussed. And I want to see what can I do with this list after I initialized it or I assigned it. So if I comment this code out, and I call the make S, this assertion will not pass. Why? first we define or we initialize the initializer list and in our constructor, and then at the end of the semicolon, because this is an R value, the destructor of the temporary R value will be called, in which in this case is initializer list S. And we can see that assert start is outputted here. But before that, we get to call the destructors, or the code invokes the constructor, enforces the destructor invocation because it is an R value after all. And when I try to reuse that list or initializer list as I defined it, in any way, shape, or form, it is completely insane, and you should never do this. This list now becomes unusable, unsafe, and illegal. Whatever word you want to use to describe it, it is bad in every way conceivable. So, what do I do in this case? How do I then actually make use of initializer list? Well, you will have to define a vector here like this and use something on heap that you're able to pass around more easily, and which will make sure to do the copies and moves appropriately and properly according to your code logic. So now that I've defined the vector list, you can also have an iteration here if you want to have more control over it. If at some point your code mutates this list or pushes back something onto this list, you would have though I don't remember how we are, let's just use an auto. So I'm gonna say start array.begin. Well, start is not equal to array.end. Start, just increment the start iterator. And I mean, this looks like a pointer, but it's really an iterator, right? So what you would do here is list pushback start, and you dereference it. Now it still looks like a pointer, but it's really an iteration in C++, as you can overload dereference operator, and you can overload postfix increment. So that's essentially how you would pick up your initializer list and use it properly, so that there is no illegal usage around your code, for the reason of being its lifetime depends just how, I mean, its lifetime behaves rather just like the lifetime of a static storage in C++. So that's why we have to really use the initializer list with caution. So another usage of initializer list is as function arguments. So if I have a function that says initializer list s arguments. So initializer list defined as arguments allows you to evaluate your function arguments from left to right. Because as you've defined your initializer list like this as a constructor, the evaluation will always be left to right. So that would be the kind of usage I would think about. But some people look at it as a multiple arguments function. I don't look at it personally like that because I can use function overloading. That would look something like this. As, let's say, if I want f1 to have 2 arguments or 3 arguments, but that is still all at compile time. But if you don't want to go through the trouble of defining or declaring all of your functions individually, you will rely on initializer list that will take care of it at runtime. And also it will be much more flexible, and it would kind of behave like JavaScript, where in JavaScript, if you define your function and it has no arguments in it, you can still call it with multiple arguments anyway. But that makes your code really difficult to read, and there is a reason for the terminology function signature or function type signature, so that you can see its return value, what it takes in, and then you can dissect what it does exactly. And in that case, function overloading would be kind of a bottleneck, but still it's not necessarily that bad, I would say, as long as I can look for my function declaration. So that's how initializer list essentially works. And there is another little point that I wanted to talk about, is that, okay, if I use it as recursion, something like this, and I have a base call somewhere in here. Now, you really have to be careful with this. While this is safe, because the life cycle of my initializer list really depends, or really resides, where I'm calling this f function. For example, I will have to not execute a code because we'll run into Stack Overflow. And then I do this S1, S2. So this usage is completely fine, as so long as you don't need your arguments to be mutated. But in order to use recursion, you have to have a base conditional call that defines where your function ends, or all the call frames should be wrapped up, and you should return from your base call. So you would definitely do something like this, where you mutate your arguments. And this usage is perfectly fine as well. So that's where and when you would use initializer list. We also talked about when not to use initializer list at all. And that is to pass it around in a struct, or pass it around when indeed its life cycle ends. And its life cycle is that of static storage in C++. Okay, that would be all. Thank you for watching. Until next time, take care.